At the instance shown, both rods of negligible mass swing with the counterclockwise angular velocity of 5 radians per second. Yay. 50 kilogram bar subject to 100 newtons of horizontal force. Determine the tension developed in the rods and the angular acceleration of the rods at this instant. All right, so because this is going to be a dual fixed axis rotation where you have this point and this point creating rotation, okay?
Mm-hmm.
The cool thing is these rods are massless. And so what they're really doing is they're going to provide you with acceleration data at B.
Mm-hmm.
Make some sense? At B and D.
Mm-hmm.
Because they're basically going to have the same exact, they both have the same acceleration. So B and D are going to have the same acceleration. They're just going to give you acceleration so that you can add it to that 100. So basically what they're saying is you're going to have the 100 giving you some sort of motion, and then you're also going to have this guy, which produces acceleration at B, giving you more motion, okay?
Mm-hmm.
All right, so let's draw and figure it out. Free body diagram. Free body diagram is just going to be the block because that's all we're considering. Boom. We've got the mass of the block pointing down. And we got the tension pointing up. Okay. So we have that. Then we have this force pushing this way. Now that can't have a reaction. There's nothing reacting against it. It's literally going to just cause this bad boy to translate to the right, which is great. So that's going to be an automatic translation to the right. Come on. Automatic translation to the right. Now, I do want to consider the effect of this acceleration, though, on the object. So I need to consider that. So what we're going to do is we're going to just say, okay, W is 5. We want to translate to alpha. If W is 5, thinking. I know normal force. I know the normal is going to help me generate my my T. But I want to see about the tangential. So I'm going to do a really quick analysis on this. A, B. We've got W equals 5. We have AT equals alpha cross R. And then we have AN is W squared R, negative R. Boom. So we're going to say the acceleration at point B is going to be the acceleration of A, which is 0. Alpha cross R. The arm is going to be negative 1.5. So be alpha cross negative 1.5. And that'll be in the J direction. This is going to be K. All right. Well, actually, I don't need those hats anymore. Then we're going to do minus W squared, which is 25. And R would be, it becomes a positive 1.5, and that'll be J. And so K cross J is KJ negative I. So it's going to be positive 1.5 alpha in the I direction minus 25 times 1.5. 25 times 1.5 is 37.5. I'm getting good at this. 37.5 J. That's going to be acceleration of B, which means that acceleration of B has an alpha. Oh, alpha. Alpha has to be.
I mean, do we want to do a moment equation?
Yeah, but we're going to do the moment equation up here. We're going to do up here. I just wanted to see how everything's correlated. So you know what? I'll just keep playing with the moment and then see what happens from there. Maybe I'll get some data. So I'll come over here. You know what? Let me box this and pull it away. Take this, move it over here. Okay. Do it again. Move it. Perfect. All right. So let's keep riding with this free body diagram. Cha-cha-cha. 100, my mass times gravity, and my TT. Everything looks like it checks out so far. So we have
that. Give me 1 second. Give me 1 second. I'm so sorry.
And while you were gone, I figured it out. You were right.
Okay.
You were so right. You were so right. And I should have neglected this till the end. Because all of this is completely useless for me. You were right. It's actually all going to come from this, all from the moment. So take a look at what I'm going to highlight. They want the tension and the angular acceleration, which means that they have to be solved together. Generally, for these types of problems, for 2D rigid bodies, the two variables that they tell you are solved together generally. And so tension can only be solved from a free body diagram. And so that means that the angular accelerations also got to be solved from the free body diagram. So the tension is going to be solved here, and then the angular acceleration is going to be solved here. So let's show you. So I want to think about the type of motion that this guy has, and that's why
Wait,
kinetic dynamics is
my
so
bad. Sorry, not to pause you, but you said really quick. You said that normally when they're given together, they're
solved together.
solved together
Yes.
for general
So,
body,
yes.
general plane.
So because they said tension and the angular acceleration, and I know that this is going to need a free body diagram, that means that my free body diagram is going to solve one side and my kinetic diagram is going to solve the other side. That's generically what happens. And what happens is after you've done enough of these, once you have a good starting point, you can kind of mentally go through the steps to figure out, oh, this would give me this as the end. So let me show you. I want you to think about what type of motion this guy has. So this is a rigid body. However, this rigid body has a simplified translation. Remember we talked about translation versus rotation versus general plane motion, right?
Yeah.
Translation has two. It could be linear translation or what I call orbit, remember? This is an orbit problem. Windshield wipers have an orbit problem. If you look at the way this will go, this object will be here and then here and then here. And so it's going to actually go along a point, some point outside of the body where that radius is going to be like that. Does that make some sense? So basically, this object is orbiting about the fixed axis point, which is outside of its body. That's what determines orbit. If the fixed axis rotation point is outside of the body. Make some sense?
Yeah.
And so what's going to happen is we're actually going to analyze this like a particle. This is going to actually be analyzed like a particle because of that. And so, because we're going to analyze it like a particle, the kinetic diagram has to be analyzed like a particle, which means the kinetic diagram is rotating, it's orbiting. And so we're going to use normal tangential coordinates. Make some sense?
Yeah.
So because of that, we're going to say it has a tangential direction, mass A tangential, and it has to have a normal direction, mass A times normal. And we know normal direction is going to be W squared times R. Make some sense? And that's what's going to give us the good stuff. That's what's going to give us the good stuff. So I'll put a normal direction here, a tangential direction here, and I know that A is going to equal, because it's fixed axis, it's got to be alpha times R. And that's what's going to solve for the alpha. And so you were right when you said to look at the moment. So we're going to do alpha. That's going to give us our angular acceleration, and this is going to give us our tension. So the left side solves for tension, the right side solves for angular acceleration, which is cute. They kind of solve separately from each other. You follow me?
Wait, so for MAN, that's mass times
Normal acceleration.
or moment. Just making sure.
Mass times normal acceleration.
Okay.
And so we'll do our X rendition, and our X equation basically just proves that mass alpha R equals 100, which is to say that alpha equals 100 divided by 1.5 times by 50. So that's going to be 2 over 1.5, which is, I don't know what, that's going to be 3 radians per second squared. I'm getting really good at figuring that out, figuring those numbers out. 2 over 3 over 2, which will give me 2 power. It's actually 1/3. So 0.33.
Maybe I'm making. So mass times alpha R is equal to 100.
Yes.
How do you know that?
Because I said
reaction
100 equals this guy, because that's the only thing in the same direction. So those are the only things. So I got the 100 and then mass alpha R. And the mass
Okay.
alpha r is just going to be, mass alpha r is just a tangential because I know it's orbiting. So that's just going to come from the fact that it's going like that. I just isolated out the part, the tangential component of that rotation. So that's where the mass alpha r comes from.
Okay.
Cool. So we got that. I shouldn't have called it the x direction. I should have called it the tangential direction. And now we have the normal direction. And so we have 2t is going up. So that's positive, minus mg. Going down is negative, and that's got to equal mass w squared r. And now you see how easy it solves once I considered exactly what you were saying. So you saw how over here, all of this information, we knew that, but it doesn't work for this problem. Strangely enough, it doesn't work out. It's not that it's wrong. It wasn't giving us the data. It wasn't giving us an answer because this part right here fell apart on us. And that happens. When it falls apart, you've got to do something else. And so we came to the moment data. I'm sorry, the free body diagram data, and that solves everything out for us. We can solve for t. T equals mass w squared r divided by 2 minus mg on top, or plus mg, excuse me. Boom. So it'll be that over 2, which is going to give me 50. And then this is going to be 25. This is 1.5. And it's going to be plus mass times gravity. I'm just going to approximate to 500 divided by 2. And that's just going to be some number. So let's figure that out. 50 times 25 times 1.5 plus 500, all divided by 2. 1187.5, which is pretty strong. That's a good amount of tension. So it's going to give me 1187.5, approximately, because I used 10 instead of 9.8. 1187.5, and that'll be newtons. Boom. And so that is our answer set. You follow me?
Yep.
Awesome. Questions on that one?
No, I think that so maybe the only thing maybe is the tension.
We found it.
But I get that. No, I was saying like the way I was evaluating, but I think I understand. It says find the tension at each rod, and it's symmetrical, right? So that's why you did it the way you did it.
Mm-hmm. If they were not symmetrical, then the tensions would not have been equal, and I'd have had not 2t here, but I'd have some t and then some other t. So I'd have 2 different t's. And knowing that, I'd have to use motion. So all the motion stuff that I was talking about, I might have had to use it then.
Mm-hmm.
But this problem, I think the hardest part about this problem was identifying this whole, looking at its resultant motion. The free body diagram was cake, but looking at the resultant motion and saying, okay, the resultant motion is not going to be a general plane motion, and it's a fixed axis rotation, but the axis is outside of the body, which actually makes it a translation. And so because it's a translation, I actually need to analyze the center of mass as if it were a point and not a body. Does it make some sense?
Yeah.
And so that's really, really important to analyze this, analyze center of mass as a point. And so look at its motion. Because now you see that you can have one of 3 coordinate systems. You can have the XY, you can have the normal tangential, or you can have the radial transverse. Any of those coordinate systems can apply to this guy based on his motion. Does that make some sense?
Yeah.
Of course, there's an I alpha associated with this, but the I alpha equals 0 because these 2 alphas are different. So I'm going to say this is the alpha of the rod, and this would be the alpha of the body. Does that make some sense?
Yeah, because it's perpendicular to the
Yes.
mass
So there's
center.
an alpha associated with this guy, and that's what we solve for. And there's an alpha associated with that guy, which is 0 because it's being held still because points B and D have the same exact motion. Same motion, which means that it's translating. And I'll put that in red. Same motion. And not only do they have the same motion, they have the same motion because it's symmetric, which proves that it's translation. But it's not a horizontal translation, it's a rotational translation, which proves that it's orbit. And so all I'm doing right now is using bits of information to prove what I made an assumption on. If you can prove it in more than one way, oh man, you've solved it for yourself indefinitely. Make some sense?
Mm-hmm.